Welcome to this lecture on electronics and VLSI. My name is Andreas Grübl. I'm working at the Kirchhoff Institute for Physics at Heidelberg University. We are doing neuromorphic computing here together with Karl-Heinz Meyer, and we are using lots of electronics and VLSI, and I will shortly explain to you some very basics of this field. So first, let's look at what electronics are. It's controlling the flux of electrical energy through electronic components and circuits of components. And these circuits of components can, for example, be complete computers like this Raspberry Pi, can be rather experimental setups like the one below here, or it can also be electrophysiological setups that are used for deriving EEGs or whatever you may like, which you might even already know. All this involves some electronics. So these are some topics of the lecture. I will start with some very basics. We will continue with Kirchhoff's laws. Then treat one RC circuit basically. Have a look at operational amplifiers, which are a very basic circuit. The transistor, the MOSFET transistor. One circuit using a MOSFET transistor is the differential pair. And then I will give you a VLSI example from our neuromorphic circuits, finally. So let's start with some very basics. Energy, as I said, is transported in electrical circuits, and it is transported by charge carriers, for example electrons. And if you have a closed system, charge is always conserved, so it is neither created in the system or destroyed. This is very important to understand the circuits later on. And if you have an electrical current, which is denoted by I, flowing through a conductor, this can be seen as the time derivative of the charge Q inside this conductor, or inside a surface element of this conductor. So if you have charge carriers flowing from left to right, then the speed of these carriers defines more or less the current. So dq over dt gives us the amount of current flowing through this conductor. You might already know this. And if this conductor is not ideal, then we have a conductor that hinders charge flow, and we call such conductors a resistor. So it resists the current flow. And inside this resistor, the electrical energy is dissipated to heat, which also results in an electrical voltage that is denoted by V across this resistor. So you can see this here. This is a typical resistor. It usually has a size of smaller than 5 millimeters. And if we have this current I flowing here from left to right, we have a drop in potential energy, which gives us this voltage in the end over the resistor. And the amount of resistivity that this resistor gives is denoted by the quantity R, which is measured in ohms. And Ohm's law now says that the voltage across this resistor is the product of the resistance times the current flowing through this resistor. And as I said, heat is dissipated in this resistor. This is in the end power, if we have it over time. And the power that is dissipated inside a resistor is given by the product of the voltage across this resistor times the current I through this resistor. And as you can see, the voltage across the resistor and also the current are directed quantities, so they have always a sign, which is usually relevant for analyzing a circuit made of these things. So what is a circuit actually? You can imagine we have a circular path for the current, and we usually have some voltage that is generated, for example, by a battery. And this causes a current to flow through some load, which might be a bulb. So the circuit is a set of electronic components and conductors that forms a closed path for an electric current. And we can have active components, like the battery, inside this circuit. And we can have passive components, like the bulb, that consume energy. The active components deliver energy to the circuit. And We also have passive devices like capacitors. We will see this later on, that store energy and can later give them back, can give the energy back to the circuit, but these are nevertheless passive components. So circuits are drawn usually using symbols for the components and straight or rectilinear lines for the connections between the components. And these connections are treated as ideal connections. So we have, for example, a voltage source for the voltage V, and we have a resistor symbol for a resistor in our circuit, and then we have a closed path that allows the current to flow. This can, for example, be a battery and a bulb. And these are some symbols for active and passive components. So we have voltage sources that supply a voltage, which has the unit volts down here. We have current sources with the arrow in this circle. The name for the current is I and the unit is ampere. We are using an A here. We can have another active component, that's the transistor. We will treat this one later on. Passive components are, for example, resistors, capacitors, or inductors. We will not so much treat the inductors in this lecture, but nevertheless, they belong to the passives. And you can see the units here. Resistance has ohms, the capacitor has farad, which is F, and the inductor has Henry. Right, so how to analyze these circuits? There are a few laws, like the Kirchhoff's laws, and before we start with these, we will first have a look how to analyze circuits. So this is a circuit containing a voltage source, a resistor R1, R2, and another resistor R3 here on the right. And we can first identify points in the circuits that have common voltages. Obviously, if you have ideal connections, all of the points on this line here should have ideal voltage, for example. Same is true below, down here. And we can mark points on these lines like this one here, point 1, point 2, point 3, and name them nodes. And nodes in a circuit are points with common voltage. We can then have branches between these nodes, like from here to here, or from here to here, or from here to here and back. And these are paths between nodes. One branch is a path between two or several nodes. And a loop is a closed circular path. That's what we call a loop. And circuit analysis in the end is now done by calculating voltage sums along loops or paths and current sums at nodes. And this is done by using the two basic laws for circuit analysis. That first one is Kirchhoff's voltage law, which is abbreviated by KVL. If we have a look at the circuit that I've shown in the previous slide, we can identify already two loops. The first loop is this one here, and the second one is that one here. And we will first have a look at the Kirchhoff law itself. So it says the directed sum of the voltages around any closed loop is 0. So if we start at 1 and end at 1 and add up all the voltages along this path, we need to have 0 in the end, which is also postulated by the conservation of energy. Because if we travel along this path, we might not gain additional energy, otherwise we would have violated the basic law of conservation of energy. So let's start at the first loop. The rule says that the sum over all paths, all voltages needs to be 0. So we start at V0 and we go along that direction. So we have a positive voltage V0. And then the voltage across R1 is a negative one because we start at plus and end at minus here. Same is true for the voltage across R2. So we start at plus and end at minus here. So we have a sum that is V0 minus V1 minus V2. That should be 0 in the end. So we can say V0 is the sum of the voltages across the two resistors, which somehow makes sense if we say our voltage source supplies a certain voltage and this needs to drop along the complete path here. We can now look at the second one, and there it's quite simple. It's a parallel circuit between R2 and R3, and we just say V2 is along our direction of movement, it's positive, V3 is negative compared to our direction of movement. The sum is 0, so V2 equals V3. And that's also more or less obvious because the voltage across the resistor 2 is the same as the one across the resistor 3 because of this parallel circuit. Next Kirchhoff's law is the current law, KCL, which says the algebraic sum of all currents flowing towards or away from one node in the circuit is always 0. This is also postulated by the conservation of charge. You cannot have any additional charge going out or in if we adhere to the principle of charge conservation. So let's have a look at node 2 around here. So the sum of all the currents, if we look at the signs, is I1 flowing in, say this is a positive sign, I2 is flowing out, and I3 is also flowing out of the node. So in the end we have I1 is the sum of I2 plus I3. Also more or less obvious, but it's good to keep this in mind. And to finish with these basic principles of circuit analysis, I will leave you with an example that you might calculate on your own. So it's just our example circuit that we had a look at for the whole time. And if we now say we have a voltage V0 of 10 volts and the resistances R1 and R2 should be equal and have 10 ohms, and we have a resistance R3 with 100 ohms here in the end, then calculate all the voltages and currents in the circuit. You can start with the current law for node 2, as we did in the previous slide, and then express all the currents with the voltages across the connected resistors. You will have then, for example, an intermediate result like that. V2 equals V0 times the expression in these braces. And I've given you the result at the bottom of the slide here. You may read it just for your reference. I think it's a good practice, good idea to do the calculations, do the math, to have done this at least once, because it's a very basic principle in electronic circuit design to do such things. What you should note here, for example, is that the current I2 and I3 have a ratio of 10, 0.47 amperes and 0.047 amperes, which is also somewhat obvious because they have a ratio of 10 in their resistance values and the same voltage across them. So that would be sort of a sanity check. Right, so that's already all about circuit analysis. We will now continue with a very short overview on RC circuits. This means that we can now add to the resistor R a capacitor which is denoted by C. A capacitor in general can store electrical charge or energy, and it is doing this, that's shown around here, in the easiest case by having metal plates facing each other, and they will accumulate charge of opposite sign on both the plates, and the charge is called Q. And obviously we will have a certain voltage also developing across this capacitance, and now the quantity describing the ability to charge, to store charge, is exactly the capacitance of the capacitor, and this is defined by the ratio of the charge Q that is stored over the voltage over the capacitor. And as I already said in the introduction, the RC circuit gives us the option to add temporal behavior to our circuits. Let's see how this goes. If we start with this circuit here, we have a capacitor, we have a resistor, and we have a certain voltage here at a certain point in time, and then we have a current I flowing. This should be our starting point. And we can analyze this starting point by, for example, using the current law. So the sum of current flowing through the capacitor plus current flowing through the resistor equals 0. And by definition, we can say that the current flowing onto the capacitor equals the time derivative of the charge flowing onto the capacitor. By Ohm's law, we can say that current through the resistor is V over R. And this, since the capacitance is always constant, can be written as capacitance times time derivative of the voltage across the capacitor plus voltage over R. And that's 0. And we can rearrange this a bit to have this simple differential equation down here. Time derivative of the voltage plus 1 over RC times the voltage equals 0. And if we now know our starting conditions like V0, we can have an exponential decay of the voltage on this capacitor. So voltage depending on time is this voltage V0 times exponential of minus time t over RC. And you all know this probably. This gives an exponential decay of the voltage across the capacitor starting at V0 with a time constant that is defined by the product of R times C. And after this time constant has elapsed, the voltage has reached a level of 1 over E times V0, which is 0.368 times V0. You should always remember that capacitances in real circuits are always there. So every input to every electrical device has a certain capacitance. And also the wire connecting to this device has a certain resistance. So you always have RC circuits all around. And if you, for example, enable a switch, you will never have a sudden increase in the voltage, but it's always, and be it as short as possible, but it's always an RC curve charging the input capacitance or discharging. That would be what you see here in this characteristic. So that's already all on RC circuits, went quite fast. Let's continue with the operational amplifiers already. So operational amplifiers are a very commonly used device in modern electronics and also in microelectronics. And it's commonly used to amplify small analog signals, like it could be audio signals, it could also be signals coming from an electrode that you have attached to some biological tissue, I don't know. And the operational amplifier in the easiest variant comes in a 6-terminal package, but actually it's only a 3-terminal device because it has an inverting input and a non-inverting input and one output. It obviously needs some power supplies which make up for the additional pins in such a package. And what the amplifier does is to amplify the differential input voltage. That's what I've written down here. So the output voltage is the product of an amplification factor times the difference of the positive and non-inverting input minus the inverting input voltage. So that means the output is a voltage source. It supplies a voltage V out, which can be controlled by the input differential voltage. So it's a universal voltage controlled voltage source. And there is also a circuit symbol for the operational amplifier, which I've given here for completeness. It's the 3-terminal device with the non-inverting input and the inverting input. To design circuits with these ideal devices, or to analyze circuits using these devices, engineers have introduced the concept of the ideal operational amplifier, which has certain ideal properties, of which I will explain only 3 to you in detail. There are 2 or 3 more which are required for a few more advanced analysis, but the most important 3 are that it has an infinite voltage gain. So actually you would expect that this is of no use, but we will later see that it is actually of quite a good use. So the input voltage is amplified by a factor that is infinite, and the input resistance is also infinite. So the resistance of the circuits at the input should be infinite, so no current is flowing into the inputs. And the output resistance is 0. So when supplying this output voltage, it can supply an arbitrary amount of current to the operational amplifier. That's the ideal properties. Infinite voltage gain, infinite input resistance, 0 output resistance. And from these rules, from these properties, one can derive 2 so-called golden rules for operational amplifiers with negative feedback. Negative feedback means that there is a signal path from the output to the negative input. That's what we mean by negative feedback. And if we have this present, we can have these 2 rules. So first one is the output attempts to do whatever is necessary to make the voltage difference between the inputs 0. It's the so-called voltage rule. So that's somehow logical, because only if the input voltage difference is 0, the output voltage is different from infinity. So that's one reason for this rule, if you have these ideal properties. So if there is an output voltage that is not infinite, the input voltage the input voltage difference needs to be 0. That's what the first rule says. Second rule, the inputs draw no current. That's the current rule. So if we apply any current analysis, we don't assume that any current is flowing into the inputs, which will be very useful for analyzing circuits that are made of these devices. So let's look at 2 basic circuits that we can build with operational amplifiers. First one would be, and that's probably the most easy one, the inverting amplifier. So we have the operational amplifier as a central element here, and we connect the non-inverting input to our ground. And I didn't introduce ground so far, but I think you can all understand that this is a global symbol denoting a global voltage of 0 volts. So if we have connection of a voltage source to our ground, that's this 0 volt down here, and we also reference our voltage at the output to ground, and we can say that all the ground symbols in a circuit are mutually connected. So we have 0 volts here, and all the grounds are connected with each other, right? So we connect the non-inverting to ground, and we have a negative feedback path from the output using a resistor, which I called R2, to the negative input, not to the inverting input. And from there we have another resistor connected to an input voltage source, which can produce an alternating voltage or an input signal or whatever we want to amplify. And to analyze this circuit, we can now apply our golden rules and the current law from Kirchhoff. So the first golden rule is that there is no current flowing into the inputs. So at this node there is no current flowing away into this input. So we can say that the current through the resistors is identical, and we call it just EI. And the second rule says that the voltage difference is 0. And if we force this input to ground, so to 0 volts, then if the operational amplifier behaves as an ideal device, it forces this input here, its inverting input, to also be at 0 volts at the ground node. So obviously the voltage across resistor 1 is exactly the input voltage, because this is also relative to ground. And the voltage across our resistor 2 is exactly the output voltage relative to ground. And if we write this down, starting with the current law, using that the currents are identical, we get this formula for the output voltage. So the output voltage equals minus the ratio of R2 over R1 times the input voltage. So using this ideal device that has an infinite voltage gain, which is of no use for practical applications, we can construct a circuit that has a controllable amplification by using just two passive components, two resistors, R2 and R1. And we don't need much more for that. And this is already a circuit that is very commonly used in very many experimental setups, I would say. And if you are an electrophysiologist or a biologist, you might know the patch clamp technique, which is used to derive currents from neuron cell membranes, from ion channels in neuron cell membranes. So we have a patch of a cell membrane here, it's a neuron's cell membrane, and an ion channel that allows a current to flow through this cell membrane. That's the way charge is transported into and out of the neuron. And then we have here a probe connected to this ion channel, and current can now flow into this probe and into a conductor that is inside this probe, and this is just connected to an inverting amplifier made of one operational amplifier and this resistor up here in the feedback path. So using this simple circuit, we can have an amplification of this current in the end, which causes a voltage drop across this feedback resistor up here, and we can even force currents to be injected into the cell by applying voltage pulses to the positive input here. That's a more advanced functionality of the system. But as you can see already with this simple circuit here, just using one operational amplifier and one resistor and a rather complex experimental setup, we can realize the electronics that are required for the readout of the patch clamp probed neurons. Another application is the non-inverting amplifier. So if you want to have an amplification factor that is non-negative, you can just connect the signal source to the non-inverting input directly. So this gives our reference here. Again, we have the operational amplifier as a central element. And in this case, we have a negative feedback from the output, again, over R2 to the inverting input. But then the inverting input is connected via this resistor R1 to ground. And we can again start by using our golden rules. At this node, the input current from R1 equals the output current through R2, because no current is flowing into the input. And now we say, due to the first golden rule, the voltage at the inverting input equals the voltage at the non-inverting input, which is exactly our signal. So the input voltage is at the inverting input as well as on the non-inverting input, and we have the output voltage here. So in this case we say that the input voltage at this point is across the resistor R1, and across, if we use the Kirchhoff's voltage law, we go along this path here. Then we can say we start with V out, have the voltage across our resistor R2, we have V in here, and then 0. So the voltage across this resistor R2 is the difference between V out and V1. V in, I'm sorry. And if we do the math, then we get this formula down here, where we have the output voltage equaling 1 plus the ratio of R2 over R1 times the input voltage. So again, using this ideal device, we have a circuit containing only two passive components in addition, where we have controllable amplification of an input signal with yeah, no additional components required. Right. As you might imagine, the operational amplifier is not a monolithic device, so it's made of several smaller devices, and in modern microelectronics, or in many cases, it's the MOSFET transistor that is being used also in the operational amplifier. There are other types of transistors also being used, but I will now introduce the MOSFET transistor very shortly. All microchips are made of MOSFET transistors, most of the microchips, I have to say. So it's the basic element, and the name is the abbreviation of metal oxide semiconductor field effect transistor. That's the MOSFET. And real op-amps, like the one you already know, consist of several tens of these devices of transistors, and complex modern microprocessors, like for example this Intel Neuran processor. This is just a picture of the core. Consists of several billions of transistors. So this is a very widespread device on our planet, I would say. And let's have a look at the cross-section of transistor. So how is the transistor being made, or where does the name come from? We have three terminals. First we have source, gate and drain terminal. And this so-called gate electrode, that's the blue rectangle here, that's a metallic component in the microchip. That stands for the name metal. And then towards the lower layers we have an oxide layer, that's silicon oxide here, for example, which is an insulator, metal oxide. And finally we have the silicon substrate down here, so that's the white rectangle. That's what would be the silicon wafer or the silicon substrate of our microelectronic device. That's the semiconductor, so that's why it's called MOS. And then if we apply a voltage to this gate up here, relative to the channel or to the silicon substrate, we will have an electrical field building up, which has an effect on the channel. I will not go into details here, but that's the field effect that is causing the function of the transistor. That's why it's called field effect transistor. The gate terminal is this metallic structure here, and inside the silicon substrate we have semiconducting areas that are treated differently. So the substrate is so-called p-doped, and the source terminal, which is this one here, and this red area, as well as the drain terminal, this is just a connection, and this red area down here, they are formed by different doping techniques. It's so-called n-type doping, and these different doping techniques have the effect that if we do it right, there is no current flux between the source or drain terminals and the substrate, unless we apply some voltage to this gate up here. And that's what the functionality of the MOSFET is all about. You may note this channel here, and there is a current that can flow through this channel. Let's have a different look on the cross section. So we can have the source terminal, the gate terminal and the drain terminal here, and we have the channel between drain and source, and the current flowing between these two terminals can now be controlled by the voltage that we apply to the gate electrode up here relative to the source terminal. And what a designer now can control is the width of this conducting area, so the channel between drain and source, that's the W here, and the distance between drain and source, which gives us the length of this channel. So these are the only two parameters that a designer can control, and these make up the properties of our MOSFET. Other parameters like the thickness of the insulating of the oxide layer here, of the insulator, cannot be controlled. They are inherent to the manufacturing process. The circuit symbol, you have already seen it in the overview slide of the circuit components, is this one here. So we have this 3-terminal device with the gate electrode, the drain and the source electrode. And the source is usually noted by this arrow here. Sorry. The MOSFET has 3 different modes of operation depending on the voltages that are applied to these terminals. And I will only cover the 2 most relevant ones. So, to analyze these 3 modes of operation, we use such a circuit here. So we have an input voltage, that's the gate to source voltage, and we have sort of an output voltage, that's the drain to source voltage. And the drain to source voltage can cause a drain current to flow through the transistor, that's ID here. So the first thing to note is due to the insulator between the gate and the channel, no current flows into the gate. And if we have no voltage applied to the gate, then the drain to source channel is not conducting. As I already said, this is due to the different doping types in the silicon substrate. And as you can see on this characteristic here, if we have a certain drain to source voltage present and rise our input voltage, so the gate to source voltage, up to a certain threshold voltage, then suddenly a current starts to flow from drain to source, and this has a quadratic dependence on the gate to source voltage. So increasing gate to source voltage improves our conductivity, and the drain current rises with the square of the input voltage, which is the gate to source voltage. So let's look at the first of the 2 modes of operation that I've promised. The device is in the linear region when the gate to source voltage is larger than the threshold voltage, and the drain to source voltage is smaller than the difference between gate to source and threshold voltage. And the current through the drain is now usually analyzed in such a characteristic diagram as I've displayed it down here. So we have increasing drain to source voltage on the x-axis and increasing drain current on the y-axis. And depending on the gate to source voltage, we get now different curves for the drain to drain current. In the linear region, so where the drain to source voltage is smaller than gate source voltage minus threshold voltage, is left of this parabolic curve here. So left of this one here. And what you see is that ID linearly depends on the drain to source voltage for small VDS. And that means that the transistor has a sort of ohmic, like a resistor behavior in this region. And this is good for digital applications. So if you just want to turn on or off a signal, we just need to have a resistor that is either low or high. And that can be done in this linear region. There is a formula for the drain current. So what you can see here is the gate to source voltage minus the threshold voltage times the drain source voltage. So we have the input voltage. Now we have a linear dependence on the drain to source voltage. That's why it's called a linear region. And with increasing drain source voltage, we have this quadratic term coming into play here, which is also causing this decay here of the curve. But initially it's linear. And the drain current, as you can see, depends on the ratio of W over L. You remember this is width over length of the transistor, and also a parameter K prime, and that's a parameter that includes things like the thickness of the oxide layer, the insulating layer, like the charge carrier mobility in the silicon substrate. So that's inherent to the manufacturing process and cannot be controlled by the user, by the designer. So what you can control as a designer are all the voltages, obviously, but the threshold voltage, that's also a device parameter, and the ratio of width over length of the transistor. The K cannot be controlled. Right, so that's the linear region where the drain current linearly depends on the drain to source voltage. We also have the so-called saturation region, and in this region the drain current does not depend at all on the drain to source voltage, which is somehow surprising because we have a changing voltage, which should also usually cause a change in current. So the transistor is in this region when the gate to source voltage is larger than the threshold, and this condition here is satisfied, so drain to source must be larger or equal than gate source minus threshold. And that's the case if we are right of this parabolic curve here. And what you can see here is that the drain current is constant regardless of VDS, and it only depends on the gate to source voltage. So that's the parameter of these curves, is the gate to source voltage, and if we increase gate to source voltage linearly, then the distance here rises quadratically because of this quadratic behavior that I mentioned in the beginning of the explanations on the MOSFET transistor. So what I already said is that the drain current does not depend on VDS. So effectively the transistor acts as a voltage controlled current source. So it supplies a current regardless of the voltage across its terminals, which is only dependent on the input voltage. And this is very useful. There is also an equation describing this behavior. We have again this manufacturing process dependent K prime halved times the ratio of width over length of the transistor times the square of the difference of the gate source voltage minus the threshold voltage. So that's the quadratic dependence of the drain current on the drain to source voltage. That's the case in the saturation region. So we have the linear region where the transistor more or less behaves like an ohmic resistor, and we have the saturation region where it behaves like a current source, just supplying a current regardless of the voltage. One very popular circuit that is made of MOSFET transistors is the differential pair. It's one of the more advanced circuits, but I nevertheless put it into this lecture because it can rather easily be understood, so no worries. And it's very, very commonly used in almost all amplifier circuits, for example, as an input stage. So what is a differential pair? So let's look at this differential pair. As I said, it's a very important basic circuit for amplifiers and comparators in integrated circuits. And the first thing you may notice is that it consists of two transistors here. I call them M1 and M2. And the point is that these transistors are identical, so they have identical widths and lengths. And since they are also on the same chip, they will have the same K prime and the same threshold voltage. We can have input signals here that are supplied by these voltage sources, and we have a current source here, so our first current source. We have a supply voltage up here, and we have two resistors connected to the drain terminals of the transistors, which should also be identical. So we have a symmetric circuit, and we can analyze this circuit now by starting to have a look at the currents. So we know that no current is flowing into the gates of the transistors, so the currents flowing into the drain terminals are identical to the currents flowing through the source terminals, and they are collected at this current source down here. So what we can say is that the current supplied by the current source, ISS, equals the sum of the two drain currents, ID1 and ID2. And you may wonder how this can go at all, but the transistors and also the current source will adjust in a way that the voltage here at the common source terminals of the transistors adjusts such that this is fulfilled. So the currents will be exactly this sum. Now let's have a look at the voltages. We can use the Kirchhoff's voltage law. We have the input voltage V1, we have an input voltage V2, and we have the output voltage, which is the difference between these two terminals. So let's start and analyze this path here. That's what I've written in this formula at the top of the slide. So it's V1, which is positive, then we go negative, minus the gate to source voltage of this transistor. We go up plus the gate to source voltage of this transistor, and then minus V2 because we go the other way around. And that equals 0 because they are connected via the ground terminals. So we can say up here V1 minus V2 equals gate to source 1 minus gate to source 2, and that should be our differential input voltage VD. And if you now say that VD equals 0, so no differential input voltage, then obviously our gate to source voltages are equal, and then the drain currents are equal, and since the drain resistances, so RD and RD are also equal, the voltage drop is equal, and the difference between the output terminals is also equal. So the symmetry of our system of the circuit gives us already this result. So interestingly, V out is independent of the so-called common mode voltage of the input, which is given by V1 plus V2 halved. So if we add a certain input voltage to both of the inputs equally, this will have no effect on our output, which still equals 0. So in the end, our output voltage only depends on the input differential voltage VD, which is V1 minus V2. And so that's already what makes up the biggest advantage of this circuit. So we have sort of an amplifier for an input voltage, a differential input voltage that transfers this by means of these transistors and the resistors to an output voltage. And by changing the values or choosing the values of these resistors, we can adjust this amplification. I will not go into detail here, but I will show to you how the currents behave with respect to each other. So this is a characteristic showing the output currents, so the drain currents, independence, so that's ID1 and ID2, independence of the input differential voltage. And since we have this current source on the tail, that's called the tail of our differential amplifier, the maximum current that can flow to any of the transistors is ISS here. And if we go to a negative extreme voltage, we will have no current flowing through the transistor number 1, that's ID1, and all the input tail current is flowing through ID2. And if we now increase the input voltage difference, one of the transistors will decrease its conductivity and the other one will increase its conductivity, but the sum can never increase ISS, and that's why they behave like this. And if you go to the other extreme of the input differential voltage, you will see that the transistor that initially carried no current now carries all the current, and the other transistor is completely off and carrying no current. And for completeness, I also want to give you the formula describing this, because it can nicely be seen what is going on here. So we have in the middle ISS, which is the total tail current half, plus minus the product of tail current times input voltage difference halved over an effective voltage that I will define, times the square root of 1 minus the square of the half input differential voltage over this effective voltage. And this effective voltage is defined as the difference between gate source and threshold voltage at zero differential input voltage. So that's more or less the voltage at the inputs if the differential pair is idle and no alternating signal is expected at the inputs. Right, what you can also see here is that if the input differential voltage is 0, then the complete term behind the plus minus sign is vanishing and the currents are equal, namely ISS half, which is also expected. Finally, the maximum differential input voltages, plus minus, are the square root of 2 times this V effective. I will not do the math, I'll just give this for completeness. So, what you can see here is that for sufficiently small differential input voltages, the ID dependence, and thus in the end the amplification, because this drain current is transformed to a voltage by the drain resistances, is linear. So we have a linear amplification of the differential input voltage at the output, and you already have seen a device where this is exactly also the case. It was our operational amplifier, and that's why also this differential pair is the input stage for all operational amplifiers. Obviously it has limitations. So the real operational amplifier, as you might have already imagined, loses some of these ideal properties that we have discussed. So last topic, as I've promised, I will give you a small example of one of our very large scale integration neuromorphic circuits. And in Heidelberg, what we mean with neuromorphic is that we are building physical models. That's not always the case, but that's what we are doing. And so we are building physical models of, for example, neuron cells, and a very simple physical model for the neuron's cell membrane, you may all know, is the current flowing into the membrane at rest. That's the neuron cell membrane capacity, that's Cm, times the voltage derivative, and that's the current flowing into the membrane. And this is equaling the product of a leakage conductance times the difference between a resting or a leakage reversal potential minus the membrane voltage. And this is realizable, that's the leak term of the leaky integrate and fire model, a very basic differential equation. And this can already be implemented by such a simple circuit down here. We have the membrane capacitance as a central element. We have a conductance, that's a resistor up here. And this is just connecting to a voltage source, providing our leakage reversal potential E leak. And this circuit can be realized by using a special amplifier circuit. It's not the operational amplifier, but it's the operational transconductance amplifier. It's quite similar to the usual op-amp. And this is used for modeling ion channel conductances in our systems. So that's the symbol that you can see up here. It's also an amplifier having a non-inverting input and an inverting input. It has an output, the green one, and it has a biasing input controlling its properties. And the property of this operational transconductance amplifier is that the output current is a product of a conductance and the input voltage difference. And that's exactly what we need if we connect this current to a membrane capacitor or to a capacitor. So if we have this capacitor in the end and we have a voltage here, EL. Then the current flowing onto this capacitor equals the product of the conductance that is made by this OTA times the voltage difference at the input, which is E leak minus membrane voltage. And that's exactly what we had for the LIF leakage term. It's the membrane capacitance times the voltage derivative of the times the time derivative of the membrane voltage. And as in the case for the operational amplifier, also the OTA is not made of only a single device, but it rather consists of quite a few transistors. In this case, it's this circuit that I've taken of one of our Neuran circuits. And one thing you may already recognize is these two transistors connecting to the inverting and the non-inverting input. And that's exactly one differential pair. And this is operating in the same way as we had it before. The only thing is that now we do not have simple resistances up here, but rather other transistors that take care of the special behavior that is required to have this conductance at the output. So, without going into details for the operational transconductance amplifier, I can tell you that we use quite a lot of them to implement our Neuran circuits. And this is a VLSI, very large scale integration, implementation of our adaptive exponential integrate and fire neuron. That's a block diagram of the circuit down here. So the central element is the membrane capacitance. And here is this leak term, which is realized exactly by this OTA that I've shown you on the previous slide. We have some circuits for synaptic input, excitatory or inhibitory. We have different other terms acting on the membrane. And this Neuran circuit obviously can also produce spikes which are fed into the network and communicate to other neurons. What you see up here is a top view of the layout within the microchips that we are building of two of these neurons. They are mirrored. And in the middle here, these are the membrane capacitances. That's one thing that can be seen. And in our microchips that we are making out of these Neuran circuits, we are using in total 512 of these adaptive exponential integrating fire neurons. So this is a picture of our so-called Heiken microchip that we are using in our brain scale system. It contains the neurons in these areas in the middle. There are synapse circuits that also consist of transistors connected to the neurons, and there are communication circuits surrounding all this. The complete chip has a size of 10 millimeters length and 5 millimeters in width. It contains about 20 million MOSFET transistors, and they make, in the end, up these 110,000 synapse circuits and 512 neuron circuits. Right. In the neuromorphic computing sub-project, we are building large systems out of these chips that I've introduced to you here. And I will now give you an impression about the size ratios between one transistor and the complete system. So we will start at one transistor. So you might recall the red areas here, that's the drain and the source terminals of the transistor. We are now looking from the top at the transistor, and this is the gate electrode. And in this technology, the gate electrode has a width of 180 nanometers, which gives us the length of the channel. That's the process parameter. And this transistor is now part of a larger circuit, as you can see here. So still here is our transistor. But now it's also connected to other transistors by metal lines that are transparently visible up here. So these are the yellow lines. And there are quite a few more metal lines which I have omitted for clarity. Usually there are 3 more layers of metal, and they are all coming out of the viewing area now, so it's a stacked setup, and we will now zoom out. So this is a transistor that's located inside one of the synapses of our chip. And during this zoom out, you can see that there are repeating structures. These repeating structures are synapses in this case. And there are, in one of the homogeneous areas, there are more than 50,000 synapses. You can now see the structure of the chip, the neurons coming in from the bottom. Now you can recognize the layout of our HiCan chip, and there are many HiCan chips on one so-called wafer. And now we are done. So this is the size of a silicon wafer that we are using in the system. It's 20 centimeters, and that's how it looks in real life. So also here you can maybe recognize the structures that are identical to the ones on the single chip that I've shown you before. So that's a silicon wafer containing 412 of these microchips, containing the neurons and the synapses. And we are using 20 of these wafers in our neuromorphic computing platform that we are having in Heidelberg. So that's the physical model part of the neuromorphic computing platform, in contrast to the multi-core implementation that we are having in Manchester from the Spinnaker project. And we are using 20 of these wafers. One is in one of these modules. Here we have 20 of these modules, 4 per cabinet, and this is the status of the platform as it has been on 30th of March 2016 when we opened the platforms. And if you want to learn more about the neuromorphic computing or the electronics involved in the neuromorphic computing, you are happy to look around on the SP9 website or also on www.neuromorphic.eu. And I thank you for your attention. Goodbye.